Well, hi there. This unit is going to introduce you to thermochemistry. If you look at the word thermo, you'll figure out from the prefix thermo that thermochemistry is the chemical study of heat and energy changes of reactions. So let's get started. Just to make some definitions clear for you before we begin, when we measure in lab the energy that transfers from one object to another, we're talking about heat, and the symbol for heat is letter Q. Now, heat is a form of energy that forms from, or that flows from, a hot object to a cooler object. We're not going to study cold or coolness, we're going to study heat. We're going to calculate the amount of heat that does move from one object to another with this equation, Q equals Cm delta T. And I'll explain all those variables to you in just a little while. Now, when you're studying the heat flow from one object to another, you have to be very specific about what your objects are. The part of the universe that you are interested in is called your system. This is the reaction that you're studying. Everything outside of that system is the surroundings. It's all the rest of the universe that you're not really interested in. It's usually the medium around your reaction to serve as the surroundings, while the reaction itself is your system. Now, the reason that we study heat is because it is predictable. The law of conservation of energy tells us that energy cannot be created or destroyed, so that means that as we study the heat gained or lost by a system and its surroundings, we can quantify it. Remember that formula that I gave you to do those calculations. So look at these two. There's a hot pack and a cold pack. What's the difference? Well, you know that one feels hot and one feels cold. So in terms of a reaction, why does an object feel hot? Well, it's because energy is being released into the surroundings. So then the opposite's going to be true for the cold pack. The cold pack feels cold, not because it's releasing cold, but because it's absorbing or taking in heat from the surroundings. When heat moves, we look at the change in energy. The Greek letter delta, or that triangle there, represents change in. So delta E is change in energy. And change in is a subtraction. So you do products minus reactants, or final minus initial. Now with that hot pack, the heat pack was releasing energy into the surroundings, so it's an exothermic reaction. The heat change here is negative. With the cold pack, it was absorbing heat from its surroundings, so the heat change of the system is positive. That's an endothermic reaction. Again, use your prefixes. Exo means out, and endo means in. And that's the direction that the heat was moving. Now here's the first graph. This is for an endothermic reaction, or the cold pack. If the reaction absorbs heat, then what's going to happen is the products have more energy than the reactants did because it absorbed all the energy from its surroundings. This is a graph of an endothermic reaction, and you can see that the potential energy of the products is a lot higher than the potential energy of the reactants. The amount of energy it takes for this reaction to occur is the activation energy. It's the amount of energy to get the reactants to convert to products. They have to get up and over that hill to form the activated complex. Now this is for an exothermic reaction, and this graph you notice is completely the opposite of the endothermic one. In an exothermic reaction like the hot pack, heat is being released to the surroundings. So the reactants have a lot of energy, and as they're converted to products, the products have less energy because it's been released to the surroundings. So in this graph, the potential energy of the products is a lot lower than the energy of the reactants. The activation energy here is a lot smaller than the first graph as well. It doesn't take as much energy for the reactants to be converted to products because they're going to lose so much energy. Now, how we measure heat is maybe something you're familiar with, but you didn't realize this is what we were measuring. The calorie. That's right, just like on the back of a candy bar or a box of crackers, you know how many calories are in a serving of that food. The calorie is defined as the quantity of heat needed to raise the temperature of 1 gram of water 1 degree Celsius. Now, different substances have different calorie amounts to them. The food industry uses what I call big calories, or capital C calories. That's actually in the metric system a kilocalorie. So when you eat the 100-calorie snack pack of chips or peanuts, you're actually eating 100,000 calories to a chemist. Similar to the calorie is the joule. The joule is just the SI, or the metric unit for heat. And here's the way they're related. 1 calorie is 4.184 joules. And that number is in your reference packet, so you don't have to memorize it. Here's that equation. Let me define each one of the variables for you. So Q is our heat. It's either absorbed or released in those endothermic and exothermic reactions. C is specific heat. Remember, I defined it for you already. I copied the definition here. Different substances have different specific heat values, and your reference tables are full of them, so you're going to have a lot of information in that packet when you do these problems. M is the mass of the sample in grams, and then the delta triangle T is the change in temperature. And just like we looked at change in energy, final minus initial, change in temperature is going to be exactly the same, final minus initial. So let's work a couple problems with this equation to get you familiar with it. Here I'm given the specific heat of graphite. It's 0.71 joules per gram degree Celsius, and I'm asked to calculate the energy needed to raise the temperature of that graphite from 294 degrees Celsius to 348 degrees Celsius. And it's a pretty large sample of graphite at 75 kilograms. So I'm going to use that new equation that we just looked at. I want to substitute in all my values, so let me show you that. The specific heat is the 0.71 number. Include all of those units because they're going to help us cancel out later. I had 75 kilograms of graphite, but remember I needed it in grams, so multiply by 1,000 to convert kilograms to grams. Plug that in. And then for my delta T, remember delta means change in. So I took the final temperature, 348 degrees, and I subtracted the initial, which is 294. Now let's cancel our units. Watch this. We're going to have this gram in the specific heat cancel with the mass gram, and then I'm going to have the degrees Celsius in the specific heat cancel with the degrees Celsius in the temperature. At this point you can multiply everything straight across, and you're going to get a heat, or the energy required, is 2.88 million joules, or 2,875,500 joules. You can do some rounding there and write it in scientific notation. It'll save you a little bit of time. Alright, one more. This time, imagine this setup as we go through it. We've got 50 milliliters of water with some acid at 22.5 degrees. And we pour it into another beaker with 50 milliliters of water with some KOH, also at 22.5 degrees. When we mix all of that in our styrofoam cup and we close the system, the final temperature of the solution is 27.3 degrees. How much heat was released by the reaction? Well, since this styrofoam cup acts as a closed system, all the heat that warms the water has to come from the reaction of the acid with the base. So I'm going to again be able to use my new equation. When you substitute in, you need the specific heat of water. Now that's not given in the problem, so you want to go to your reference tables and look it up. You'll find that the specific heat of water is 4.18 joules per gram degrees Celsius. The mass here is the mass of all the water in that cup, so be careful that you don't just put 50. You've got a total of 100 milliliters of water. And remember, for water, every milliliter is 1 gram because of the density of water. So we have 100 grams of water. And then finally that delta T, final minus initial. So take the 27.3 and subtract 22.5. Watch your units cancel out again. Grams with grams, and degrees Celsius with degrees Celsius. When you multiply straight across, you'll find out that this reaction is releasing 2006.4 joules of heat. Now, where does the 2006.4 joules of heat go? When it's released from the reaction, it goes to the water, and that's what makes the water in the styrofoam cup warm up. So hopefully that gets you started with thermochemistry. I've given you the units to measure heat with, we've looked at endothermic and exothermic processes, and we've looked at how to calculate the amount of heat that moves. Thank you.